internal signal. So I need, these are port, but this is not a port, and this is not a port, it's internal connections. So I need to declare them. Okay, so what I'm saying is that for the NOT, I'm using A as input port, P as output. So here I take a wire that I call P, okay? And I'm connecting it at the output of the NOT. But this P is also called here as input of this end port, okay? So P is shared between the two, output of NOT, input of AND. Then I have the other end has A and C, and the output is called R, okay? The output of this end instead is called Q. So these are all internal signal, okay? Then Q and R goes to OR, and the output is Z, okay? So I have described the connection between the module with the port mapping, okay? And take into account that the encoding is positional. So the first is the first port that you have declared here. So the first is X, the second is Z, okay? So I'm connecting A to X, P to Z, okay? It's positional. Please. What?
Does the compiler respect this separation, or does it just compile into the same thing if we had written it in just one?
So well, depends on where. It keep the hierarchy until the optimization of the synthesis, basically. Then it will flatten it out, because we need, it will flatten the hierarchy, unless you specify with some attribute that you want to keep the hierarchy. Then, because in the optimization, he will also, well, in this case, it's so simple, but also in this case, so what you expect that, how many loot you expect to use. So one doesn't want to have one loot for NOT, one loot for AND. So at the end, you want a single loot that basically does the full function. If you ask to keep the hierarchy, the compiler will keep 4 different loot during the synthesis, but usually it flattens it out. So this is a practical way of writing it. When you want to recycle part of the code, it's for you for typing less code, let's say, but the compiler will ignore it, will flatten it.
What about the names G1, G2, G3, G4? Do you use that for anything?
Yes, these are labeled. So this is the name that I give to the component. So that was actually the component name, and this is the instantiation name of the component. So this is G2, and this is G3 for me. So I'm giving a label. This is useful. I think it's also mandatory, so you need to give a label, because then when you have messages, warning errors, it will recall it to the name of the instantiation component. So yes, please.
You already mentioned that I'm not convinced about entities. So you said that entities are just functions in C++ or something, but they are also data translated to hash of a physical circuit.
So entity here, we are using basically, so this is our big entity, top module is called, and then inside we call component, and component are just other sub-entity, let's say, so of our circuit. So here, this is a full VHDL file for me. This is a full VHDL file. They must be in different .vhdl file. And then here I'm just putting all together. But this, I mean, I was calling them function just for the idea that you can reuse it. So this is an entity that you can reuse many times. So you can call it many times. Also, so I think in a while we will see also this, you can have for loop. So if you want to call it many times, this end, you need many end, you can generate it with a for loop. So here I didn't use it because it's trivial, but.
When you generate the big string, those codes to the entity or in different physical parts.
Well, no, actually no. In this case, what we were saying that actually this is a hierarchy that you have in your code, but the compiler will flatten this hierarchy. So it will build a single circuit, and it will apply optimization. So even if if you compile any single entity here, any single entity, it will use one loot for every entity. But when you put it all together, probably these 3-4 functions stay in the same loot. So it will use only one loot. Thanks.
So each of these blocks is a separate file.
Yes.
And you have to import it so that you can find it, or?
Yeah. So we can see now in Vivado how to do it. So here we are. No, it's not this one. Sorry. Okay. I think. Oh. Let's open here. So this is, well, also let me put it in Git, but this is the full HDL file with the input output, and this is the combinatorial function. So if we look at the hierarchy, I think I lost the hierarchy with this Windows. So I will give you this this file. So this is the combinatorial function written in this way, and this instead is the combinatorial function that's called the submodule. So I have put all the file in the same project. You can reuse also the same project yesterday. There is no problem. The only problem is, so how to do it? You just add the source, design source, and then or you create if you want to type it, or you add the file, the one that you download from Git. I can send you immediately. But what I want to say is that in the hierarchy you will find it here. So now you have to decide which one to compile. So which one is the top for you. So in this way, with a right click on it, you can set as stop module. Okay, set up stop module is the one. So now it will update. So I'm choosing this one as stop module. He will build this. He will synthesize this. When I uploaded, I added to the design the and or not port, you cannot see here because they are inside the combinatorial function too. Okay, if I open it, you can see it in the hierarchical view. So let's open it. This is the combinatorial function too, where here you have the declaration before the begin. I'm declaring that I want to use this component called end port. Then I want to use the or port that I have in another file. Then I want to use the not port that I have in another file. Then I want to use the signal for connecting them. And here I start the port map. Okay, you can do it positional, like in the slide, or also in any order you want, recalling the entity port name. So this means I want to connect the X port of the not entity to the port A of my top module. I want to connect the Z port of the not entity to the P signal of the port of the top module. Okay, so you can do it positional, A, comma P, or recall the port name of the entity. Okay, both are valid. Probably this is easier to read, to recall the name of the port. So, and also you don't have to specify in the correct order of the port. So same for the end. I call it port 2. I call port 3 another end. So look, this is the same module, the same entity. XYZ is the name of the end port. ACR are signal of the top module or port, and that's it, and behavioral. So when I look at my, see here, I have the name of this port 1, port 2, port 3. It's actually this name, the label of the component, the instantiation name, and then the name of the entity later. Okay. So let me put it on Git so you can also try. So well, before, let me start the compilation so we don't lose time. A combinatorial function. So we can run linter on this. In meantime, I put it in Git. Okay. Yes, I moved the file. I'm sorry. Okay, so it pushed. Let's reload. Okay, so we can open it. Yes. Yeah.
Something I thought about, so the other day, I think we mentioned, part of the population, and the reason why the population is this low is because it involves some simulation that the expert of the area.
Yeah, it's an optimization problem because we needed to optimize the routing basically.
So that made me wonder, is it possible that we compile the very same code twice and we get different?
Yes, it's possible. So in the older version of Vivado, actually was the standard one because it took different seed for each compilation. Now they have improved this, so usually if you keep everything as it was, it take also the same seed, so it will end up in the same compilation. But if you change a comma, nothing, it will have a different result. Yes. Yeah. So this is the what we expected as compilation. Let's go ahead to see how many loot are needed for this. So let's also build the synthesis. So this is the interpretation of our VHDL. Exactly the same schema at the blackboard. But now let's see the schematic after synthesis. We don't expect to have any more the distinction. We expect to have a single loop that does everything. So let's see. Yes. Exactly. So when you declare component and component name, if it is the name of an entity that it has in the project, he will recognize. Yes. Okay, so that's our three variable function. So one loop was enough, okay, for implementing everything. So everything is inside the loop. So let's see now in the hierarchy. I lost the hierarchy. Here we are. Now I change the top module and I set as top the other combinatorial function, the one that recall all the others. So let's see the RTL analysis of this. Okay, so it's very similar to the previous one. So now he understood that we have a component instead of logical port that we have declared. We can also look at what there is inside to this. So if we open, we find the port actually. So, but from the VHDL, he understood that we are using a submodule basically, okay? But now, so we can go through the synthesis and see what is the expected. So we can close the previous one. So now we expect exactly the same synthesis, please.
Just a question, are we supposed to do this in parallel right now or just listen to you? Because both is just kind of hard.
Okay, as you wish, as you feel more comfortable, yes. So here I'm doing a sort of tutorial. You can look or try as you prefer. Then I will, in a while, I will give you an exercise so you can do it yourself, and I will not do anything in parallel. So this is the new synthesis, the same as before. Okay, so all the simplification in the code will be applied in the same way as before. Okay. So this is the hierarchy part. We can go ahead. So let me open. Okay, so let's see. Let's move from this logic to from Boolean logic to actually numeric value, so arithmetic. Ah, so small. Okay. So of course, so we are dealing with hardware. So at the end, also the numeric, it's a combinatorial function. So also the arithmetic at the end is a combinatorial function. If we want to write this directly in the hardware way, what we have to do is to think about the truth table of an adder. Okay, so what is an adder? So an adder, it's basically a structure where you add one bit to the other, and then you have the sum of these two bits and the carry that you propagate to the next bit that you want to add. So the idea is to build this adder as elementary cell that each cell add one bit. So in this case, we are adding the bit are A and B, and C is the carry, the previous carry, if there is a carry generated by the cell before. S is so the first three are input, S is an output, is a sum, and C, I plus 1 is the next carry, so the carry that I'm propagating to the bit. So this is a very simple way of summing to bit. So it's the circuit way of summing to bit, let's say. So if you look at the truth table, means 0 plus 0 plus 0, because I have to sum also the previous carry, result in a 0, 1 plus 0 plus 0 result in a 1, again 1. Here I have 1 plus 1, it's actually 2, but 2 doesn't exist, so it's 0 carry 1, okay? So it's just a sum of a single bit. If I resolve, I ask what is the Boolean function for S and C plus I plus 1, so my output. This is the canonical form of the function, and here is the simplification that I can do with using Boolean algebra theorem. So at the end, this is what I want to do. Yes, please.
Just a question. Why in the last row, 1 plus 1 plus 1 is like the carry?
Yes, so this is 3 actually, right? So you can imagine that this is written in as 1, 1 is 3 in binary. But, so if I do 1, 1 is a 2, yeah. So 1, 0, carry, it's like, so it's 0, the result is 0, I carry 1. Here, 1, 1, 1, the result should be 3, so I write 1 and carry 1, so 1, 1 is the result. So you can see it like the result written in binary with this. The carry is the most significant bit. The sum is the less significant bit. So this is a 0, this is a 1, this is a 2, this is a a 1, this is a 2, this is a 3. So, but okay, I mean, I'm doing this just for sake of connecting the Boolean circuit with the arithmetic, but this is a task for the compiler, not for us. Okay, so it's just for learning purposes. So this is the circuit generated by this equation. So if I want to do another, I need to design this circuit. So this is the sum. Sum is a concatenation of XOR. I'm doing the XOR operator between A, B, C. Carry, it's a concatenation of NAND between all the others element input. Okay, so that's the circuit that we need. This is for adding 1 bit. So if we take this as elementary cell, what we have to build, it's a sort of a chain of this elementary cell for adding. This is an adder for 2 numbers with 4 bits each. Okay, A and B are 4-bit numbers that I sum 1 bit at a time, and I propagate the carry. Okay, so if you write this, okay, let's try to write this in VHDL. So let me open Vivado, and also let's see what is the code of this. So this is okay. This is also an exercise for recalling the module, because this is a modular design. So we have one single adder that we propagate for many adder. So let me open the file. Open. This should be this one. Okay, so let's start with the 1-bit adder. So 1-bit adder, it's the circuit that we have seen. It's a Boolean circuit exactly with, as the other one. So it has 3 inputs. This is C in, the incoming carry, C out, the outgoing carry, so on and so forth. I'm declaring in a Boolean way the circuit. This was XOR, XOR, and then was a combination of AND and so on. And that's it. This is the one single cell. Let's suppose now that we want to connect them together for having the 4-bit adder. Okay. So what I have to do why it's not increasing this? Okay. So now let me make it floating and then disappear. Sorry, there is no way. Okay. So now the top module, the 4-bit adder, is adding 2 standard logic vector this time, not 2 standard logic, because they are 4-bit. So we declare them 3 down to 0, okay, 4 bit each. Cin is still 1 bit, the carry is still 1 bit. The sum, it's 4-bit output, again, because we have one sum for each bit, but the cout is 1 bit only, okay? So inside the architecture, we declare that we want to use the 1-bit adder that we have defined before in another VHDL file. That has, I just copy the port as the entity declaration. But here, basically, I just change the name between entity and component. But it's just a cut paste. Then I need this signal for connecting them, the carry. So you remember that the carry was connecting one after the other. So the first carry, I will use an internal signal for being the first output carry of the first bit will be the input of the second. So I need to use internal signal. So I call A1 the first block that takes bit 0 of A and B, produce bit 0 of the sum, taking input Cin, that was the port, and cout, it's an internal signal going to the next bit. So if you look, this cout becomes Cin of the next 1-bit adder. Okay, so we are doing the chain. This it's working on bit 1. Okay, produce Y2. Again, this is consumed Y2 by A3 that is doing the third. So on and so forth till the last. The last is taking Y3 as Cin, and cout is the output port of the module. Okay, so this is a hierarchical way of building the 4-bit adder. So now what we would like to do is to go further, and we would like to have a general structure that does an n-bit adder. So this is the for loop, basically. So we need a way of generating a component and connect also them together. So this is a new statement of VHDL that I'm telling to you that is called the generate. So it's a sort of for loop, basically. So let's see this. Okay, so first of all, now our n-bit adder, it has to be, it has to have a parameter that is our n, basically. So how to introduce a parameter? There is this possibility to have in the entity what they call generic. So generic, it's actually it's really a parameter that your module can have. Okay, so in this case we define a parameter called n. Okay, that for us is the number of bits that we want to sum. We can give a type, can be a standard logic, can be an unsigned, an integer, a natural, like in this case, a positive. So there are many types in VHDL. So natural is integer, positive, basically, and also 0. I think it's complete. It's in natural. And then you have always to give a default value of this parameter. So why you need a default value? Because this is a parameter of your design, but in hardware there is no dynamic allocation. So it's not possible to change the circuit. So I needed to build the circuit. It's not possible to change it runtime, the circuit. So when I build the circuit, I needed to decide the parameter. I cannot increase the parameter runtime. I needed to fix it at compile time. So I needed to give a default value that will be taken by the synthesizer during the synthesis. Okay, so here I'm defining a parameter generic with n that by default is equal to 4. So now the port, we have two input ports that are standard logic vector n minus 1 down to 0. So it was 3 down to 0 before, now it's n minus 1. The same with the sum, okay? Now let's see. Component declaration, I still declare that I want to use the 1-bit adder. This didn't change. So here it's more practical to write it in this way, because before I was using a fixed label for the signal, y1, y2, y3. So here I need n plus 1 labels, basically, okay? So I call it, I use a standard logic vector, so a number of n plus 1 bit signals, okay? So I declare that I want to use an internal signal that is composed by n plus 1 bit for propagating the carrier. Okay, so let's have a look to this. So now my scene, I map it in the first bit of my internal signal. The last bit of the internal signal, I map it to Cout, okay? Then, let's see what is this statement. So this is the generate that I was telling you before. So before I declared for time, I instantiated for time. Now I'm putting this in a generate that is a for loop for instantiated n time. So this is, we need always labels. So this is the label address generate, is the label of the generate, of the for loop. And then we have the label of the component instantiation. So this is a for loop from, from I equal to 0 to n minus 1. So we generated n time. We generated what? We generated the 1-bit adder component. And this is the generic, it's the port map basically of this 1-bit adder. So parameterized with I, basically. So you will have n of this. So A0, B0, Y0, sum 0, Y1, and then another one that is A1, B1, Y1, sum 1, and Y2, okay? So on and so forth, you will have the 4 component. And that's all, okay? So this, it will implement a 4-bit adder or 8-bit adder, depending on the generic that we have fixed at the beginning of the entity. So now the question could be, what is the purpose of doing this if I have to fix in any case? And yeah, please.
Just a question, like how does it work with timing in this case? Because your iterations are not dependent on each other, right? So they don't run all in parallel, or do they?
They are in parallel. So this, it's well, that's a good question. This is a for loop, but it's very different from a for loop in C++, because the result here is a parallel. So it's completely unrolled for loop, let's say. So this generates 4 entity or n entity that run in parallel. There is also the possibility, we will see later, of doing for loop serial for loop, but it's another environment, another statement. So what is the point of doing this declaration if then I fix n immediately to 4? This is basically for reusing the code, because this is a 4-bit adder, but let's assume that I use it as a sub-module inside a bigger project, a bigger circuit, okay? I can use this same entity as a component in a bigger circuit, fixing it to 4, but I can reuse it another component, same entity, fixing it to 8 or to 32. So I can have many other with just changing one number. I reuse the same VHDL code, okay? So when I instantiate an entity as a component, I also do the port mapping, but I do also what is called the generic mapping. So I can fix each port and I can fix the generic each time that I declare the component, okay? So let me, first of all, put the chargers, otherwise. Okay. Well, let me also put in Git all the file. Okay, so there is a folder called adder now. Yes. So, well, I don't know if it's worth to go through this. Okay, so let's see now. This was just an exercise for looking at how it works from the circuit point of view. Now let's see how to use the arithmetic for generating exactly the same circuit. So if you want, then you can verify this, that the adder that we have done using the Boolean function of the addition will generate the same circuit as the adder that we do in a much easier way using the arithmetic functions. So first of all, we have to take into account that here we are talking about modular arithmetic. So what does it mean? That usually we declare how many bits we want to use. So here we have the fine granularity of the single bit. It's not like C++ where you have to declare 8-bit, 16-bit, 32-bit. So you have byte, the granularity, or even less. So you have few data type that you can use. Here we can use a data type custom, so 2-bit, 3-bit. We have seen the standard logic vector. So depending of the number of bits that we want to use, we end up to use a modular arithmetic on that number of bits. So when we are at the end of the numbers that can be represented with that number of bits, we wrap up. And if you have 3 bits at your disposal, if you do 7 plus 3, it ends up to be a 2, okay? So it's the modular arithmetic. Or 3 plus 6 it's 1. So it wraps up automatically. You don't have to handle yourself. For the negative number, it's possible to represent signed and unsigned number. For the negative number, the convention is to use the 2 complement. So probably you know what it is. It's just a way of encoding a negative number. So you can recognize the negative number from the first bit, that is always 1, positive always 0 as the first bit. And it's a practical way of encoding it. So the rule is, if you want to build a 2 complement, the rule is to complement all the single bit and does do the +1. So this is the rule for generating the negative. Anyway, this is handled by the compiler. It's just that you know that at the end, the result is this. When you want to use a signed notation, due to this, you need to remember that you need 1 bit more, basically, because you need 1 bit for the sign, basically. So if you want to encode in 8-bit, usually with the signed, your range is 0 to 255. In negative, the range, it's always 256 number, but centered around 0, so you can go up to 127, 1 bit less, basically, of representation. So now, what are the functions that we have at our disposal? So we have always worked with the standard logic vector. So this is the type at our disposal thanks to the numeric library of OHDL. So from standard logic vector, we can say, I want to give a representation, numerical representation to the number that can be unsigned or signed. And this is just a cast, okay? So we moved, we cast our vector v to an unsigned or to a signed, okay? Simple. And with the cast, we can also come back after, because remember the port of the entity, the top level entity must be standard logic. You cannot have unsigned. You can have unsigned in the inner module of your circuit. You can keep the unsigned also in the port, but at the end, when you have to interface with the pin, you need a standard logic vector type. So you can come back at the end of your calculation. There is also the possibility of using more high level, let's say, type, like integer. But here there is a big difference between integer and unsigned. The difference is that you lose, using this kind of number, you lose the bit granularity. So now unsigned, you know that if you build an unsigned coming from a standard logic vector that is 3 down to 0, also your unsigned will be 3 down to 0. So the number of bits is preserved. When I move to integer, I'm losing completely the notion of bits, how many bits is needed for that signal. So this is why I can do a conversion from unsigned to integer, simply like that. But when I go from an integer back to an unsigned, I need also to specify the length of the unsigned. So I want to encode this integer in a n-bit unsigned, okay? So here we have in the data type the information regarding of the bit number. In the integer we don't have. So we are going far from the hardware, basically. But if we want to do numerical operation, unsigned and unsigned are enough. So we don't have to go up to integer. We go up to integer, for example, in some cases where we want to address, so for the address of a vector is an integer. It's not an unsigned. So if we want to convert our signal in an address of another standard logic vector, for example, then we need to go up to integer, but it's quite uncommon. So let's see how to do an addition with unsigned arithmetic, so the equivalent of what we have done with the logic port. So this is the same declaration, I think. We have the n generic natural defined to 4, standard logic vector, and down to 1. So it's the same entity as before. Now let's look at the architecture. So now the architecture it's much more compact. So what we have here, it's basically, so from where we start, let's start from a result, okay? So we are doing an addition of two numbers. So if this number that are called A and B are 4-bit numbers, how many bits do you expect to have the result? It cannot be 4. I mean, it could be, but you are truncating the sum. It should have 1 bit more. So if I can truncate it like I'm doing here at the output port, but internally, when I store the temporary result, I need 1 bit more. So this result signal, it's an unsigned for me, but with 1 bit more for accommodating the full result of the sum that has 5 bits in this case. So for me, this result, it's the sum of the unsigned A, unsigned B, and the carry. But VHDL asks you that all the things that you sum up has the same number of bits. So I need to concatenate a 0 in front of it. So this now is a 5-bit, this is a 5-bit, okay? So I'm adding 2 5-bit. And the carry, I'm defining it as a 5-bit as well, okay? And it's seen concatenated with 4 zeros. Okay, so this is interesting to see. We never see this way of writing. What does it mean? Here I could have written, so here I wanted 4 zeros, basically. So I could have written this way, what we have seen yesterday, basically. Okay. Or so this is the initialization. So actually the initialization operator is this one. So I can do this, it's perfectly legal. But I want to be more generic, because if here I change n to another number, this remains statically to 4. Instead, I want a way of writing it that doesn't depend on the number of bit. Actually, it's all zeros I want. And this, it's another way of writing. So let's make an intermediate step. I can write this. I can do something like this. 0, it's defined as the first bit of 0, I want to be a 0. The second bit of 0, I want to be a 0. Third bit of 0, I fix it to 0. Fourth bit of 0, I fix it to 0. Okay, so this is, there is a comma and there is a comma. This is a way of fixing, it's completely equivalent. This is a positional, this instead is, I address each address of the vector independently. Now, there is in VHDL a keyword that is called others. Why there is an others word? It's for this kind of notation, because I want the first bit fixing to 1, the second to 1, and all the others to 0. So that was the idea of this keyword. If I use only others, it means that I'm not fixing any of them, but all of the rest. Okay, so the other option is doing this. Others to 0. Okay. Okay, please. Yes, exactly. So this notation, it's also, let's make another kind of constant. For example, it can be bit 0 fixed to 1, and then others fixed to 0. Okay, this is the way of defining.
Does it work also others? I mean, like for the intervals?
The range, there is another keyword that is called the range. Yes, it's possible to define some range. So I can take, it's not a keyword, it's an attribute. I think an attribute, yes. So you can define a range of addresses of this constant to be something, and another range to be something else. Yes, it's also possible. Okay, so this is a way of having 4 zeros or n zeros, let's say, n zeros in this case, and then I pad my scene with all zeros in front, and I build carry. So then I can do the sum of this 5-bit or n plus 1 bit element in, and they goes in result. Now, sum is a standard logic vector, so I need to convert back from unsigned to standard logic vector. So here I do the truncation. So I just take the 4-bit of result. I keep apart the 5, the 5th. I take the less significant 4, and I convert it with a casting to standard logic vector. And this is my sum. The 5th is the carry. Okay, so my carry out is the 5th bit of result. Same code if you want to give a try, you can implement this should give exactly the same circuit as the one that we have done before. Let's do a step more, same code for signed now. This take into account the 2-bit, the 2 complement for the negative. It's very similar. It's very similar. The difference is that we declare this intermediate step as signed instead of unsigned. And here, for the carry doesn't matter because it's always or 1 or 0. Here, since are signed, I cannot pad it with the 0. I need to pad it with a 0 if it is positive, with a 1 if it is negative. So here I take the n-1 bit of the B port, okay? And the same for A. There is only this tiny difference, but then the other part is completely the same. There is a function that helps you to automatically do this. That is called resize function. It's inside the same library, and it will handle this difference. So here I did it explicitly just for noting it, how powerful it's VHDL in going to the details and to the optimization of your code. But of course, this is something that if you are doing a complicated circuit, you don't want to handle by hand the difference between a 0 or 0 and 1 for the negative. So there is a resize function that will pad basically your signal with a given number of bits that can be 0 or 1 depending if it is assigned or unsigned. So this will be handled automatically. Okay. So I think maybe we can take a look to the VHDL, but I think I already put it in I lost. Okay. It should be this n-bit adder. Yes, so this is the same code. Okay. So 15 minutes. Let's see the last example. So then after the break, we can I can give you an exercise so you can work alone for a bit. I just want to show you the last thing of VHDL. If I find it. Well, we can stay directly on the. Well, you know what is a 3-state component? Let's recall it for 3 states. Okay, so normally a driver can have 2 values, 1 or 0. So can drive a line on 1 or 0, but sometimes you want to have like in a bus, like what we said yesterday, we want many drivers on the same line. So that's why we use a component that is called 3-state. So it can have also the high impedance, the Z, okay? So the 3-state, it's usually have this symbol with a control here. So the control is for declaring if this is an output or an input. So if here you have a control signal, here you have A and B. So normally this drives B with the value that there is in A. When C it's, for example, 0. When C goes to 1, then B goes to Z, okay, high impedance. So how to use this component? So there are basically two ways. This one is on a bus, so every driver of this bus that access to this bus implement a three-state. Okay, so all has to be in Z, in high impedance, apart from the one that's right. But also, this is a common component when you use a bidirectional line. So suppose that I have only one pin dedicated for communication with another device. And if I have two pins, I can do one for sending and one for receiving. But if I have only one line, I need to implement a bidirectional communication. So in HDL, there is also the possibility of doing a port, declare it is in-out. So there is the in, there is the out, and there is the in-out. But in this case, I need to use a three-state, or a couple of three-state actually. So the schema that you commonly use for a bidirectional line is this one. Okay, so here is the control, A and B. Okay, so this means that negated. So when this is enabled, this is not enabled, and the opposite. Okay, so in this way, either I'm writing on the bus, either I'm reading. Okay, so when I'm reading, I'm disable the writing and the opposite. So this is the common way of doing bidirectional link. So let's see this three-state component. So if I want to model in VHDL a three-state, I need three ports, input port, output port, T. I'm sorry, I used another convention. T was the control line, I call it C, and AB, sorry. So input, output, and control. Well, pretty simple. Input goes to output when control is 0, else high impedance. Okay, that's the model of a three-state. This is the behavioral way of describing a three-state component. So now, why I'm doing this exercise? Because I want to show you how to use the instantiation. So this is a description, behavioral description of the three-state, but three-state is a primitive in my hardware. So the FPGA has really three-state buffer inside. So instead of declaring here with this line, the compiler will infer a three-state. So we can, we can also give a try while I'm talking to run. There is the other option. It's declaring that we want to use a three-state ourselves. So we don't want the the compiler infer from the code, we want to instantiate it manually. So while it's compiling this tree state, I can show you the difference. So how to do it? First of all, if we want the catalog of the primitive, we can open the language template. Here, we can look for tree state buffer. Please writing correctly, tree state. And better to choose the VHDL. Ah, they changed it. They removed this. Oh, using process use one else. Wow. Okay, so it's not this that I wanted to show you. Sorry. Output buffer tree state. So we should see in here. Oh, boof. Okay. So you need to know that it's called output buffer tree state. This you have to look it in the manual, the name of the primitive. But here you have the sorry, this is probably Verilog. Okay, so we need an Artix VHDL, so single-ended. So here you have the component. So what does it mean? This that if you want to instantiate in your code a tree state, you need to instantiate the component that is called output buffer. So here we don't have the entity because the entity is inside the vComponent primitive library. So this is the library that Xilinx gives to you with all the primitives. So there is a documentation of all the primitive inside the library. And here you can find it basically the snippet to cut and paste to your code if you want to instantiate this primitive. So look, there are the three ports. There is a little explanation of what they do. And then what is the advantage of using this? That you can, so while in the other code where you make the compiler understand from your code that he has to instantiate a tree state buffer, here that you do by hand, you can also set some of the parameter with the generic map that we have seen. So this in the entity are generic. When you call the component, becomes generic map, and you can fix some of this parameter in your code. So if I want to use, in the other case, I don't know what the compiler will have done. So probably there is, I mean, for sure there are default value of all the three. But if I wanted to change this, I need to declare it in this way. I cannot make the inference. I cannot leave the compiler to infer the component. So this is the output current that I want to use. This is how fast I want my rising edge of the signal. If I want a slow signal or fast signal, very squared wave. And the IO standard, here I can fix directly CMOS 33 like we did it yesterday. So copy paste this snippet of the code in my VHDL, just really copy paste, and that's it. So if I compile these two, they will result in the same component, but here I could fix all the parameters. Okay, here there is a problem with the constraint file. Test design. Let's see if we have it. Well, at the end, it's just this output buffer, okay? It's our tree state. If you want to compile the two, you will have exactly the same result. So once again, let me tell you how to do it. So if now you want tree state 2, so the other description, just set a stop module, and you can relaunch the synthesis. Okay. Good. So we can have a break, I think, and then start to play yourself with the FPGA. Okay, we can resume the session. So if you want to take a FPGA, please pick up your FPGA so we can So let me tell you what which exercise we want to do now. So we have seen yesterday actually the multiplexer, what it is. You already know it's a way of mapping one output, one input, one of the many input to only one output. This is an 8-to-1 multiplexer. 8-to-1 means that we need a way of addressing 8 lines. So we need 3 select line, okay? So these are 8, this is log, basically, log 2 of 8. So 3 select line for addressing them. So for encoding 8 possibility, we need a 3-bit. So that's the point. There is also another component that is called the multiplexer that does the opposite operation. So it connects one input port to one of the output of the 8 output. Still need the 3 select line. It's exactly the same concept. So To encode the multiplexer in VHDL, it's quite easy. We can use the same structure that we have seen so far. So this is a 4-bit 4-to-1 multiplexer. So 4 input port, 1 output port, and 2-bit for select lines. Okay, so we have 4 cases basically. So depending on the select line, we assign to the output the input. Okay, we need always to make an else, even if, so here you can say there are no other possibility. That's not true, because the select line can be uninitialized, can be X, can be Z. So there are also other possibilities. So we need to specify what happens in else case. So I put it in the Git, the file for this. If you want to try to implement, please go. I will not spend too much time on this. I would rather ask you to do another exercise to build the MOOCs yourself. So write a demultiplexer and possibly make it generic like we did it for the other. So this is a demultiplexer, n bit, 1 port of n bit that goes to 4 port of n bit. So we are demultiplexing not only 1 bit, we are demultiplexing a word of n bit. Okay, so this word of n bit, this standard logic vector n bit, should be mapped to one of the 4 n bit depending on select line, so that you have to take into account. So this is the first point to do. So this is generic with n. Then the task is I take my generic entity with that does this demultiplexer of n bit, and I instantiate it in a top module that declare it n equal to 4. So make the generic mapping of my generic demultiplexer and fix it to 4. So it is instantiated in a generic mapping. So it does the port mapping of the top module connecting to the output of input to input and output to output, but then it fixes also to 4 and in order to implement it, to synthesize it. Here I ask you to simulate also. We didn't arrive yet to simulate, so don't worry. But the next step is to also write the constraint file or take the master constraint file and fix the location of the input output. So a practical, a convenient choice is to use for the input the 4 button of the board, and for output the 16 LEDs that we have at our disposal, because we have 4 LED normal and 4 LED RGB that are actually 12 LED, because each LED can be 3 colors. So we can consider it as a 12 LED. So in total we have 16 LED in our board. So these are 4 buttons, 4 LED, 4 LED, 4 LED, 4 LED. Okay, we can map it in this way. And then for the select line, we can use 2 switches that we have in the board. So in this way, depending on the switch, we can switch on 16 different LED using 4 buttons. Okay, so that's the task. Please, it's your turn. Okay, welcome back. We can go ahead, I think, with the more interesting part of HDL probably. It's when you introduce the clock. So till now we are done only combinatorial stuff, no clock at all. Now we can start to see what happens when we add flip-flops. So just to recall what we have seen last time. So in the FPGA, there are only one kind of flip-flop that is called the D flip-flop. So there are other kind of flip-flop, maybe you have heard it, SR, JK flip-flop. In the FPGA, there is only D flip-flop that are the simplest flip-flop. So the equation is this one. So the output Q is equal to the input D, the following clock cycle. So it's updated. So Q, it's what was the previous clock cycle, the input D. The truth table is pretty easy, and this is the symbol. So there is the flip-flop comes also with a reset port, not only a clock port, but also a reset for resetting it asynchronously. So what does it mean? That if I add a reset line, that the reset can come even between two clock cycles. So if I start to reset here, I reset my flip-flop here, the output will go to 0 immediately as soon as the reset line is there. This is the asynchronous reset. There is also the possibility of making a synchronous reset of the flip-flop. So depends on your code. So we will see the difference in the coding if I choose a synchronous or asynchronous. Synchronous reset means that even if the clock arrives in between, the output is updated at the next clock cycle, like a normal flip-flop operation. So how to encode a flip-flop? Very easy. Still, we have a 3-port clock in, D in, Q out, as usual. Here we have to use a special environment that is called process. So what is process? Process is an environment for making the code serial, not anymore parallel. So whatever there is inside the process, so here we have the architecture, then the begin, and here we use this environment process and process end. So inside the process, what is executed is more similar to what you are used to C++, Python, so it's sequential. So here you can use also if statement that outside of the process are actually the when else statement that we were used before. So they use also different statement because the environment is completely different from what there is outside of the process. So the idea is this one, that I use an if with a keyword that is the rising edge. So if there is a rising edge of the clock, then I make the copy of input to output. So that's pretty easy. So that will result in a flip-flop. So Now, I put a code that is a bit more complex, but it's just an example. We go to spot only the on this code a part for underlying what I mean with a serial environment. So a serial environment. So this is a priority encoder. Doesn't matter what it does. It has its own entity, its own architecture. This is the priority encoder used described without process, so in a concurrent way. Doesn't matter. And these are two versions of the priority encoder architecture done with a process. So just to make you to spot the difference, so look at here. So in this environment, in the process, what I would like to do, it's basically to assign. So let's look first at this if. So I want to assign valid to 1 in all this if statement, else if statement, apart from the last one when I want valid to 0. So what I can do, it's basically set valid to 1 at the beginning and not repeat it inside each else as usual, and put a 0 only at the last one. So if you do this outside of the process, it's an error because you are driving the valid line with the two different values at the same time. So it's a conflict if you do it outside of a process. Inside of the process, this is read serially. So the variable are updated only at the end of the process. So here the variable is set to 1, then later is set to 0, and the real update happen at the end of the execution of the process. So this is a legal way of programming. If you instead do it in outside of the process, this means that the signal valid is assigned to 0 and to 1 at the same time. So something wrong. Okay, so the idea is this one, that you can have many, please. No.
I'm just curious about it. Each of the ifs there takes one block. So does it take one block?
No. No. So the exact here there is no clock actually, but okay, because the process you can put it also in. So it doesn't matter. It could be also a combinatorial process. So this will result in combinatorial logic if there is no clock. As soon as this line, if at the beginning of your process there is this line, means that this is not only combinatorial, it's what combinatorial, in this case there is no combinatorial, but if you, here I put, for example, A and B, it's a combinatorial port, a logic port, followed by a flip-flop, because we are inside the clock rising edge. If here I don't have a clock rising edge, so it's fully combinatorial. There is no flip-flop here. The result is just a loot.
That doesn't mean that all the instructions between beginning and end are executed.
No. Here we are inside of the process. So to understand what I want the compiler does, I need to execute one after the other, and only at the end I will assign to valid the value that it has. So and my lookup table should do this basically. So I'm behavioral describing what the lookup table should do, the logic. But suppose that you have if rising edge of clock, and then inside you have all this. This will result in still one single flip-flop. and the if, so the flip-flop is the y, so the output y will be the output of the flip-flop, and all this logic given by the if will be combinatorial part before the flip-flop. Okay, so whatever you put here, or if condition, or anything that will be assigned to Q will be combinatorial, and the Q will be the flip-flop, basically, the output of the flip-flop. So the idea is that in your code, you can have many processes if you want, and all the processes are executed, meant to be executed serially and updated the variable only at the end of the execution. But if you have many, they are concurrent. So all the processes are concurrent among them. So you have to pay attention that you can have interaction between the processes. So if a process write a variable, this process can read the variable in parallel. Okay, and there is no semaphore or fancy stuff for regulating the processes. So it's up to you to pay attention to use flag or whatever to be sure to not write at the wrong time, read at the wrong time a variable. And also it would be much better from a code perspective to use variable if the variable is global, because till now when you declare the variable before the beginning of the architecture, this means global variable for all processes. It would be better that only a process writes on this variable and all the other reads. Having two processes that write on that variable for sure will end up in a conflict because they are working in parallel. If you want, there is the possibility of having local scope variable, and it's here. After the process, you can define a signal here before the beginning of the process, and this will be a signal only visible inside the process. If it is here instead, like we did till now, it's actually common to all the processes, so it's a global variable. Okay. So let's have a look to Vivado. For seeing an example of this. Too short. Well, I have this simple flip-flop. It's basically not more than what there is already in the slide. Sorry. Here I added the reset also. So look, this is so you are in a process environment. Begin, if rising edge, then if reset equal to 1, then output to 0, else output to D. So this is a flip-flop with a synchronous reset. Why it's asynchronous? Because if there is no rising edge, this reset is not even read. Okay, so it's ignored. The reset, if a reset change without the change of the clock, the reset is not taken into account. So this is a coding of a synchronous reset flip-flop. If I wanted to do a asynchronous reset, then I should have done this before the rising edge. So if reset equal to 1, then Q equal to 0. Else if rising edge of clock, D go to Q. So this is the asynchronous reset.
Can you maybe repeat what, so the argument doesn't pass the process? What does it? Here is clock.
This one?
Yeah.
Okay. This is called the sensitivity list. So it's not an argument of the function. It's a list of signal that enable the process. But first of all, I have to make so I have to specify that this it's something that is used only in simulation. The synthesis ignore this sensitivity list. So when you synthesize, it doesn't matter what there is inside. When you simulate, instead, the simulation has to know when to execute the process, basically. So you have to put this in the sensitivity list, a list of signal that triggers the execution of the process. So whenever clock change, the simulator executes the process. If clock doesn't change, it doesn't execute. But of course, this doesn't have any meaning in the synthesis because the synthesis execute always. So it's parallel, completely parallel. Instead, for the simulation, we needed to specify the sensitivity list. So in this case, I would put only clock because if clock change, then I would execute. Instead, in the case I'm trying to do on the fly the difference, if reset 0 as if something like this, right? Probably I have too many and if. Yes, oops. Here we are. So here it's an asynchronous reset. So whenever there is reset, I want to put at 0 the output, and then as usual, copy the clock one clock cycle later. In this case, in the sensitivity list, I should have added reset because I want my simulator execute the process also when reset change. That depends on the design. It's not easy to understand this. So usually synchronous reset is safer because you have the possibility of resetting all your process at the same time, basically. Asynchronous reset rely on the delay also of the reset. So if the reset is not propagated inside your FPGA in the same way, you are resetting actually at different times. But it's true that the reality is asynchronous many times. So a button, when the user press it, is really asynchronous. So depends if I mean, 99% of the time, I don't care if there is a difference of few nanoseconds between my pressing, and so I would declare as well as a synchronous reset. If really I care that whenever the reset comes, the output should be 0, then it's an asynchronous, but it gives you many other problems for the fact that you need to pay attention on how you distribute the reset across your design. If you have many processes with many reset, you are not fully sure that they will be resetted at the same time if it is asynchronous. So a synchronous one is much safer. Sure.
The precision timing is anyway bounded by boundary.
Yes, yes, definitely, definitely. So there are very few cases where you really need the reset to act immediately. Okay, so that's the flip-flop. We can, well, we can come back. Okay, and then let's see other example. So what we can see, it's a shift register that is a collection of flip-flop actually. So let's have a look to shift register. Maybe here. Close it. Oh wait, sorry. Okay. So still 1 bit for input, 1 bit for output, reset and clock. So now I want an internal standard logic vector of, let's say 8. I want a shift register along 8 clock cycle. I declare it a standard logic vector. Then after the begin, I can do this. So this is a process. So a process with the rising edge clock. So this is an example of asynchronous reset. So not the best example. Asynchronous reset equal to 1, then all my internal register is put to 0. Okay, all the output of my chain of a flip-flop. If rising edge, then the input goes to the first flip-flop. And here I have a for loop that assign each flip-flop to the next one. Okay, so this it's so the first goes to reg 0, then we have reg 0 that goes to reg 1 that goes to reg 2, until what? Until this is a way to say the left bound of register vector register. So this one. So the left bound is 7. The right one is 0. Okay. If I say the left is it takes 7. If I say right, it would be 0. So it's a generic way generic of saying this. So if here I put n, and then n defined as a generic parameter, then this will be basically n. Okay, so it's just to make the code a bit more generic. So this is 1 to 7 basically. I loop, and every line like this in the for loop will be translated in a flip-flop. So this is a flip-flop. This is a flip-flop. So how many flip-flop there are? So this is one. It's 1. These are 7 flip-flop. From 1 to 7, they are 7. So in total, 8 flip-flop. So now I need to put the output of the last flip-flop to the output port. Here we are. So the last one, the 7th, goes to the output port. So why this is out of the process? Because if it was in, would have been translated in the 9th flip-flop, in another one. But I already have 8 flip-flop there, so I don't need another one. So I do this connection like a wire. So it's not anymore a flip-flop, it's just a wire because it's outside of the process.
I'm a bit confused. So you say that this happens sequentially, but so for example, if you put the input into register 0, then you put it to 0 first. Doesn't the 0 have the input already, and then you just move it? Like it's not moving the thing, but just putting the input into that. Moving the same thing.
Yes, so here we are putting the input to the 0 and the 0 to the 1. So you have to distinguish what there is on the left and on the right of the arrow. So on the left is the current clock, on the right is the previous clock cycle. So this register 0 that goes to 1 is different than that one. It's not the same. Yes,
Zero from the previous.
exactly.
So what do you mean by sequential? If it's just all
No, with sequential, I mean that so let's redo it here because the for loop make a bit of confusion maybe. So the for loop in which the L is completely unrolled. So you have to imagine like seven statement, 7 line all together. So here we have something like this. Okay, and then others doesn't matter. So what I mean is that variable b, it's updated only after the sequential execution of this process. So only at the end. So only when I am at the end, I will update variable b. This is why this b is not this one. It's the previous one. Okay, so in this sense. So C is not equal to A. So we have to read it in this way. So C is equal to A at the next clock cycle.
Everything between 953 and 958, everything in between happens in one clock cycle then.
Yes.
Nice.
Yes, exactly. Exactly. Everything in the from the clock if, so rising edge of clock to the end of the process, it's only one clock cycle. So it's yes. Here we have to pay attention when we use this, that the logic cannot be so much because we have to take into account that everything that we put here, so even with just one statement, has to be executed in one clock cycle. So we have to take into account, so we have the power of having the control of a single clock cycle, but on the other hand, we don't have to, if we have to do a complex operation, we have to break it in many clock cycles. Otherwise, we will not fit in the timing.
How do you break it
into different clock cycles? So either you, so basically now what's the point is that so if I do this, well, this is an AND with D, okay, and this is OR with E, okay. Let's assume this. So this will result in something like, so it's true that this is a single clock cycle, but it's a single clock cycle for B and single clock cycle for C. So this will result in A and D flip-flop, and this is B. Then here I have an OR with E flip-flop, okay? So it's a single clock cycle for B, a single clock cycle for C, okay? So my logic is break down into two parts. Different would have been if I do this. Sorry, A and D or E. This is a single flip-flop with the two-part or all this logic in front of the flip-flop. And depends if this is a lot of logic, it could not close the timing. With this technique, I break it down into two flip-flop. Please.
If the timing is not correct, does it say that the synthesis level?
No, implementation. After implementation, you will see here. We still not have seen it because we never declared the clock in the constraint file. And now also we can see how to do it. Design runs here. Worst negative slack, total negative slack, worst all the slack. So this is the setup time violation, all the time violation, and you will get a number in red. Usually you get a number black that says I can match the timing by few nanoseconds or just a picosecond. If it is red, it's the contrary. I cannot match the timing by that number of nanoseconds after implementation. Yes, let me show you. Okay, since we are here, let's see the constraint file, if I have any. Well, you have also the master constraint file. There is already the timing constraint. Here we are. This is the clock. Here we are. So the first line is the one that we are used. Set property in pin package to E3, so it's the pin location and the electrical standard. But then we want to say that this is, sorry, there is a missing part that we associate to the clock port. Get port CLK, okay? Get port CLK. Then there is another line that says, this is a special pin, is a clock. So I want to create a clock of, I give the period, this is 10 nanoseconds. Okay, by default, it's in nanosecond, the clock. I give a name of the clock because for the reports, it will tell me if I have many clock, I want to give a name. This is add, so I'm adding a new clock. And this waveform is optional. It's for giving the duty cycle of your clock. So it's not, the duty cycle is the times, the clock is 0, with respect to the time the clock is at 1. So this is 50% duty cycle. So means that this is 5 nanoseconds and this is 5 nanoseconds. Okay, 5 nanosecond high, 5 second low in a 10 nanosecond period clock. So of course, if your clock is done like this, still this can be 10 nanoseconds, but the duty cycle is different. So you would have declared 0 to 2 for the high, and so the waveform parameter would have been different. But if you omit it, it's a 50% duty cycle. And that's it. So this is the way of specifying the constraint of the clock that you find in the constraint file. Yes, please.
Those 10 nanoseconds are going to be 50 cycles. Those are the numbers you choose, are numbers you get from these.
Yes, exactly. So the number here, you don't choose it because it's the manufacturer of the board that chooses it. So in the board there is, well, we can here there is a local oscillator. So this is a 100 megahertz oscillator. that is connected to pin E3, so the one that we declare. So we needed to say to the compiler that we are using that clock. If we want to use a 200 megahertz clock, we cannot change there. We need to change the board, unfortunately. So, but there is the possibility of using the PLL, the component that is inside the FPGA. So we can route that 100 megahertz clock to the PLL and configure the PLL to divide it by 2 and make it 200 megahertz. So this is also possible. So I can increase the frequency of the clock inside my FPGA with an analog component that is the phase locked loop. So we will see this later, how to do it. So you don't have to be stuck on a single frequency, you can increase it. Let me talk about still remaining on the shift register. And that's it. Still remaining on the shift register. Now I want to propose you another code that actually doesn't, I mean, it make not a single bit to shift, but a vector of bit to shift, okay? So instead of shifting a single bit, I'm shifting a word of a given number of bits, 8 in this case. So just to understand that it's my input is not anymore a standard logic, it's a standard logic vector 7 down to 8. So I'm shifting 8-bit 32 times, I think, is the length of this shift register. So internally, now, before internally I had a vector of the length of the shift register. Now what I want is an array, basically, because I'm shifting 8-bit many times. So I want as a structure a vector of vector that is a custom type in VHDL, because there isn't this data type. So I have to create my own data type. So I create my own data type. I give a name, register type is an array 0 to 31. So the length of this array is 32-bit of standard logic vectors. So each element of my array, it's a vector. So this is a 2D vector, so an array, a matrix, basically. So this means that one dimension is 32, the other dimension is 8, okay? And then I assign this custom data type to register reg, to signal reg. And here it's pretty much similar to before. So before reg was assigned when there was a reset, when it was assigned to other than 0. Here we are in 2 dimensions. So it's other of others that goes to 0. So this is a vector of all zeros that will be assigned to all the position of the array, basically. So we need to initialize all of them to 0. Then what happened? Well, very similar to before. So now the index, it's the index of the array. It's not the index of the vector. So we have a vector that goes in one cell of the array that is a vector. So we can do this kind of assignment. So here doesn't change so much. So here, for example, I used right instead of left before, because for some reason I declare the array with the 2 and not the down 2. So this is left, this is right. Okay, I want to go until 31. So all this freedom of VHDL, it's nice, but it's very confusing for the code, of course. So it's error prone, let's say. And that's it. Then the last one vector goes to the output vector. Okay, so this is so let's see the last example, and then I would give you an exercise. So I want to show you a counter, a simple counter. So a simple counter here. So this is just what I want is just an output port. It's just an output port that change every clock cycle. It increments the number. So it's a 4-bit counter, so it will count from 0 to 15. So when all the 4 bits are 1, 1, 1, 1. And then automatically it roll back because it's modular roll back to 0, wrap up to 0. So here I use an unsigned signal, 3 down to 0, with others 0. So it's initialized to 0. So the process is quite easy. So it's a must have a rising edge of clock because I want my output update every clock. And what I do, it's just count equal count plus 1. This I can do because it's an unsigned, okay? If I cannot do directly plus 1 in a standard logic vector because I didn't assign the numerical type. So I do it in an unsigned, and at the very end, after the process, I convert the unsigned in a standard logic vector for connecting it to the output port. So this will result in actually 4 flip-flop, okay? Because count is a vector of 4. So it's like having count 0 assigned to count 0 plus 1, count 1 assigned to count. So, I mean, they are 4 assignments, okay? It's a compact way because they are vector, but actually they are vector of 4 bits, so they will result in 4 flip-flop, okay? So with a bunch of logic ports in front of them for making them change it in the correct way, okay? So, but the code, it's pretty simple, okay? So what happened if I would have put this line here inside the clocked process? I would have done a counter followed by a register. So I would have delayed by 1 clock cycle my output. So probably nothing would have happened. I mean, I would never realize this, but count is counting every clock cycle. And if count is 3, my output would be 2 because it's delayed by 1, because this would have inferred a further layer of flip-flop, okay? So instead of putting it in output, there is no delay between here and there, okay? Between the left and the right. So it's a direct connection. It's a wired connection, no flip-flop in the middle, okay? Yeah, it's outside of the if statement of the rising edge. So if I put it inside, still it will, so inside of the process, but out of the if rising edge, still will have worked in the same way. It's only if I put it inside the if rising edge, then this will have translated in a flip-flop. Okay. Fine. So let's see the exercise slide, and then I will put also on Git all this stuff. I don't have it, sorry. Let's see. Sorry. Before moving to the project, let's see also a simulation. Maybe now it's useful to take a look to the simulation of this counter. So, and to write a small test bench for this. So I can propose you a test bench. So here we have a test bench for the shift register array, and we should have also a test bench for the counter. So let's have a look to the test bench for the counter first. So you remember what is a test bench? It's an empty entity. So an entity that contains your block under test, and also the input and output will be generated inside the test bench. So my entity test bench has no port, okay? Now I instantiate the component counter, that is the component that I want to test. Now I need to provide the signal to counter. So counter actually has only clock and output, okay? So what I have to do is to declare an internal signal called counter, an internal signal called counter output, and then I can, that has the same dimension of the output, and then I declare a constant of type time 10 nanoseconds. That is my constant period. Then after the begin, I instantiate my counter with a port map. So this is the port of the counter that is mapped to my internal signal clock. The output port of the counter is mapped to my internal signal counter row. Then I need to provide the clock. So I need to generate my clock. So this line, it's something that you can use only in simulation. It's not a synthesizable VHDL, but in simulation you can use a assignment like this. So clock is not clock after half clock period. So every time it's changing clock, not clock, clock, not. And this is like a wait, okay? Wait for half clock serial and then change. So very easy. Here we don't have many things to specify. This is enough for our purpose. So we need to spy this to signal basically. Clock we provide it because it's an input. Counter row, it's what we want to spy in the simulation. So if I also here I can have many test bench and I have to declare a stop. So I want to simulate this. Here we are, test bench counter that contain my counter. I run the simulation. Here you have the choice, depending on at which level you are of the implementation, you can have behavioral, post-synthesis, or post-implementation. We do the behavioral simulation. And that's the result. It's a waveform. Okay, it has simulated for 1000 nanoseconds. And so here the clock that I have created, a clock that, let's make a zoom here. Okay, so this is between 65 nanoseconds and 75, so it's 10 nanosecond period, and the counter, so the output of my counter is increasing each clock cycle. So by default, this is in hexadecimal notation. So you can also see all the 4-bit that are the 4-bit of the counter. If you want in decimal notation, you need to specify the radix to be decimal, unsigned, for example. So then it goes up to 15 and then wrap up and roll back to 0. Okay. Yes. So in the test bench, we needed to provide all the input port to our design. So this was a super easy test bench because actually our component has only one input port, that is clock. So this we needed to specify. Output port, in this case, we are only watching it. So we are only checking that is working. So I needed to assign, in any case, to signal to them because I want to spy this internal signal of the test bench. But I needed to provide only the clock. So I'm not providing any counter row because counter row is an output. So let's have a quick look to this other test bench, for example, the test bench of the shift register. So the shift register had more, it has also another input port and reset, a clock in. So I needed to provide all this signal. So here there are the internal signal. I give the same name, doesn't matter. Constant period as before. This is the port map. So this is the port of the component. This is the internal signal of the test bench. I gave the same name, so it's straightforward. Same assignment for the clock. But now I give this process for the other signal. Here I'm giving only there are two processes. Okay. So the first, it's an assignment of reset. So reset at the beginning of the word goes to 1, then wait 200 nanoseconds, put it at 0, wait forever. So if I don't put this wait, remember, sorry, maybe I didn't tell you, the process is like a loop. So you remember if rising edge, so this if rising edge is continuously checked, not only once. So everything inside the process is continually scanned. Okay, so if I don't put a wait here, this will loop. So we stay to 1, then wait, then goes to 0, stay to 1, and so on and so forth. So I needed to, if I want just a single time reset, I needed to put the wait at the end. This is instead for the input. So here I am assigning at the beginning of the computation, I am assigning to the input a given, no, sorry, here I'm exploiting the fact that the process is a for loop. So I'm each time the input. So at the beginning, input D, it's probably 0. So depends on how it has been initialized here. Let's have a look. Yes, so at the beginning was initialized to all zeros. Then after each clock cycle, I'm increasing it by 1. So I'm transforming it in an unsigned, so I can do the +1, and I'm transforming it back to a standard logic vector, so I can assign it to the input D port. Then I wait for 1 clock period, and I change it again. So every clock period, I'm changing it. So let's have a look to this. What happened? Okay. Very good. Yes, so let me close the simulation. Close simulation. So it was the previous simulation, I guess, that was blocking. Okay. So still, okay. So this is the, so I had 2 parallel processes. So reset is behaving like described. So waiting, it was still, it went to 1 at the beginning, then after 200 nanoseconds goes to 0 and wait forever. This process is stuck. The other process was doing this, basically. Or doing the increment of the input. Okay, so I'm incrementing by 1 this line. So this is 8-bit. So if we look at in unsigned, it's probably long. So it goes up to 255. So what happened here? That here we have the first output. Okay. So let's put it also in unsigned. So we have the first output, 21. So let's have a look here. 21 is the first coming in after the reset. So whatever there is during the reset is ignored by our shift register because we had this asynchronous reset in the shift register, so was putting it to 0. Then 21 enters, and later goes out. So later, how much? 32 clock cycle, because this is the length of our shift register. So this, it's basically delaying our output of 32 clock cycle. Okay, so that's the expected behavior. So the simulation is meant for checking this. So the exercise that I want to propose you is the following. Make a counter able to increase by 1, or, I mean, here I am choosing a different way. So this counter can be increased by 1 or by 3 or decreased by 1 or by 3, depending on the switches. So if you want to increase it by 1, this is normal behavior. If you want to use a switch, it decreases by 1. With another switch, it make other computation. So this is a mode of operation. And then you can use the LED for looking at the counter. So it could be a 4-bit counter, and you can use the 4 LED for mapping it and see the counter. That's the exercise. So I would start with a simple counter, and then you can increase, use the shift and increase the functionality. And now you can also simulate. I will put on Git all the test bench of the normal counter and so on.
We're getting a bit distracted. Yeah, thank you. Just like more.
Okay, so I put a folder called the sequential. All the files that we have seen are there.